Hello, thank you for participating in our webinar where we will discuss valves for dry and wet solids and chemicals that provide tight shutoff without clogging. I am Jim Haldeman, Business Development Manager at the Lesman Instrument Company. We are joined today by Chris Mitchell. Chris is a training manager for Red Valve and has nearly 40 years of experience in teaching others about various valves, including pinch valves. Chris has supported customers of Red Valve products around the world, helping customers to best apply the proper valve for their application. You have all been muted. If you have any questions, please enter them in the question box in the toolbar below. I will see them. I will ask them on your behalf. The webinar is being recorded and posted on the Lesman website for others to listen to at their convenience. With that being said, I will now turn the presentation over to Chris.
Hi, everybody. Good morning. Thanks for attending and thanks for Lesman setting this thing up for us. Let's just jump right in. So basically, this is pinch valve 101. So the big question is, and we still get this from time to time, what exactly is a pinch valve? And as it says on this slide, at its most basic, a pinch valve is a valve that uses a very ruggedly constructed flanged rubber tube as its flow element. If you look at the graphic on the left, that tube isolates the mechanical parts of the valve from the process. This thing is built just like a car tire. So when you see the dashes, the lines, that's nylon, Dacron, polyester fabric. And these sleeves are built just like a car tire. Is also known as a pinch sleeve. So we will interchangeably call it the tube, the sleeve, the pinch sleeve. But this is the heart of the valve and what really constitutes a pinch valve. So why do we use them? Pinch valves are really what we're dealing with typically with pinch valves, and what the technology is slurries and dry solids. So large, sharp objects, thick viscous sludges, slurries. Basically, the valve provides a no maintenance or very low maintenance product. Valve's fine for throttling and modulating on something like brick, sludge, influent. We also operate in mass flow where materials are dry. In chemical application, where you might require an exotic metal in a conventional valve, in many cases we can avoid that with a very simple rubber material. And they're also used for isolating internal valve parts from the flow medium beneficial. So if you have a very aggressive process that has a tendency to eat up your seals and mechanical parts in traditional valves, we'd be able to help you with that. So traditional valves, and there's nothing here to slam any of these valves. They've been around a long time and they do very well. But ball valves, plugs, butterflies, diaphragm valves, even valves like knife gates, all of them have a couple things in common. They're going to have packing, they're going to have seals, they're going to have journals, they're going to have flow elements like a plug, a disc and a butterfly, a bowl that's right in the flow stream. And considering that our major market is slurries and dry solids, those obstructions tend to get worn out pretty quickly. And a pinch valve is designed to avoid all. So in traditional valves, as I mentioned, you've got a ball, a plug, a disc, the valve body in a weird diaphragm right in the flow stream that's going to get impacted by these high solids bearing processes. So some of the issues with traditional valves, a lot of them, especially when we're talking about slurries, require regular exercise and maintenance. generally because grit and small fines fall out into the packing, the journals, the grit seals, the mechanical parts in general, and cause those valves to seize up over time. All these valves that have a mechanical component in the flow path causes turbulent flow through the valve. And where we have turbulent flow with the slurry, that results in excessive wear. So what we're trying to do with a pinch valve is keep flow as laminar as possible. And that pinch sleeve allows us to do that. And again, all these conventional valves are susceptible to solids collecting around all the mechanical parts. The pinch valve avoids that type of thing. When the flow elements and seats start to wear out, you start to get blow by in the valves. Pinch valve doesn't have that issue. In fact, for a pinch valve to fail, you've got to wear completely through the pinch sleeve. So it's not like a traditional valve where if you lose a little bit of the seat or you lose a little bit of a disc or ball, you'll start to get leak by. Pinch valves do not exhibit that type of behavior. And all styles, and it includes pinch valves too, if not properly maintained and exercised, will be affected by increasing torque values over time. So here's the upshot of that comment that becomes very important. Let's say we're talking about a plug valve, and the grit seals, the journals get all plugged up. Over time, that valve starts to get stiff. It becomes difficult to operate. If you designed an actuator, say an electric actuator, to operate that valve, the torque values to open and close that valve may have changed over time. With a pinch valve, because the pinch sleeve isolates the process from all the mechanical parts, those torque values will be the same 10 years from now than they were the day you took it out of the box. So that becomes a big issue. So traditional wear, we showed a little graphic here. Basically, when the slurry comes through at velocity, it takes a little piece of the flow element itself, and it takes a little piece of the seat, and that causes blowback. The pinch valve concept originally was very simple, and what you're looking at here, it actually goes right to left. So this pinch sleeve is open, and you'll see nothing inside that flow stream. The material is able to go through unimpeded, very smoothly, non-turbulent. When we start to close that valve, it starts to close around the solids until finally we effect total closure via closing the pinch sleeve. That's the entire concept of a pinch valve. If you can imagine putting a soda straw between your thumb and your index finger and pinching it, that's exactly how a pinch valve works.
Chris, we have a question.
Yeah.
We have a question referring to that last slide. So is there like the question is there some type of minimum viscosity or thickness for the material? I think what he's alluding to is if you have a really viscous slurry and then you crimp down on it, wouldn't you get some material between the two pieces of the soft seat actually? And
yeah, great question. Tremendous. Okay, so you see this graphic on the left? And this is just showing this pinch sleeve closing. Can you see my cursor, by the way?
Yes, we can.
Okay. The way we're showing this is the minimum amount of air pressure, for instance, to close the sleeve. It's just where it's touching. When you apply generally the 30 to 35 pounds over the line pressure you need to close this sleeve, it's going to start to close across the length. Anything in there is going to get wrapped up in that sleeve. If there were welding rods, it'll close around welding rods, rocks, you name it. It'll close around them. Of course, if you had a 2x4 stuck in there, that would be a different story, but it would nonetheless try to close around it. So as long as we can move that fluid through the valve, we'll be able to close around it.
Great.
Does
So
that answer it?
it does. So the seat actually forms around whatever might be between the two and creates the seal.
Yes,
Awesome.
correct. So it's a little bit, it's hard to show because we can only look at it 2D. But if you were to say, throw some rocks, gravel, whatever into one of these valves and watch it close, it'll start to close across the length of the valve and actually form itself around the obstruction. So as long as you can push a viscous fluid through, and it doesn't matter if it's glue or if it's paste backfill from a mine, if you can get it through the valve, this valve will close.
Great. Thank you.
Yep. So what are the potential issues with pinch valve technology? So one of them is there is no standard for pinch valve. So all the pinch valve manufacturers that are in the world have been resisting getting together and writing standards for a long time. So as you look around the pinch valve offering out there, you're going to see all kinds of face-to-face dimensions, just all kinds of different designs. So there is no standard. We're limited because of the elastomers available to us by temperature, and usually around 350 to 375 degrees F, and we're limited by pressure based on valve size. So to give you an example, that 48-inch valve is rated for 30 psi. A 24-inch valve, we can get up to 150 psi. Keep in mind that what we're dealing with the pinch sleeve, even though it's very ruggedly constructed, is actually a balloon, right? So you can keep putting pressure in it till you tear it apart. And one thing about rubber, we build all of our pinch sleeves in open. So rubber, having a memory, wants to stay open. If you keep that sleeve closed, say an isolation valve, for 6 months, a year, that valve is going to want to naturally take a step in the closed position. Now, if you have adequate line pressure available, that will open that sleeve back up. So we're constantly mindful about how we're using these valves. So this is what the pinch valve sleeve construction looks like. This material we're showing you in white, we're only showing it to you in relief so that you can see the different layers of material. So this material in white would be one of the elastomers that we have available, and this would constitute the wear surface of the pinch sleeve. We use a full face flange. It does a couple of things. One, it self-gaskets the valve. So you don't need gaskets to get these valves installed. It's a rubber face flange on either end, and it allows you to avoid gaskets. Then, after that, we use rubber impregnated fabric as the support and the layers to get this sleeve straight. So what you end up with a smooth inner layer, you have this bias ply fabric, and again, it's just like the construction of an auto tire. Then it gets an outer wrap, and that outer wrap can be also one of these elastomers, depending on the style of valve we're using and how much effect we might get from ambient conditions. And we'll look at a couple things there as well. But that's generally the cross section of a pinch sleeve. If you were to take a section out of a car tire, it would look much the same.
Chris,
So
we do it.
you will never get to see this unless you visit a manufacturing facility. But I threw a little bit of this in there too.
Chris, we had a question about bolting on that flange. Is there like a recommended torque when you install that? I mean, can you tighten it too much? What does red valve state there?
Okay, so there are in the IOMs bolt torque recommendation. I will tell you from experience, you cannot really over-torque me, right? But I will say this to you, because that's a rubber flange, one of the caveats and warnings is raised face mating flanges cause us a problem. So what happens is if you mate this pinch valve up to a raised face mating flange, you are liable to cut the face of that rubber. So we always recommend a flat face flange. If you don't have that, you're basically putting in a metal washer to make up that difference. But
Great.
yes, there are recommended bolt torques.
Thank you.
All of these fabric layers that constitute the strength of the pinch sleeve, really the most important part of it, and where you see all these terminate, is right here at the flange, where the flange meets the tube. Because remember, we're going to pinch this tube, all the stresses are going to come against that flange. And then when it's all over and it's all built out, it gets wrapped in a tape. The tape very precisely shrinks, becomes our mold. Everything goes into a vulcanizer, comes out, everything gets finished. We drill the flanges, finish it up, and the sleeve goes into a valve body. So the sleeve itself is really the guts of the valve. Now, this hand fabrication process that we use allows us a lot of flexibility. So here's a standard sleeve for you. There's a recipe for it. A 4-inch sleeve has so many layers of the wear material. It has so many layers of fabric. And then we can go to a double wall sleeve. So for instance, a standard sleeve gets you 5 years. A double wall sleeve being 2 to 3 times the thickness of rubber is going to get you probably 10. So wear is just abrasion and time. Cone sleeve. This is really unique. We're going to talk about this in a little while in a little more depth. 95% of the valves we use for either throttling or modulating control are going to have one of these cone sleeves in them. Same type of construction, but this time we're characterizing the flow as it passes through the valve.
Chris,
So generally speaking, when we operate in applications that are open, close, on, off, we're using full port, full bore sleeves. For control applications, we're going to use cones.
We had one question.
Now, because we hand build these on mandrels, we've got a lot of flexibility. So essentially, if a standard sleeve can take, say, 150 PSI, we can get 720 out of it by building a high pressure sleeve. And basically what that means is we're putting more fabric throughout. And that's how we accomplish a 300-pound class valve. So rubber selection. This is really the key to the whole thing. So basically what we're doing is checking chemical compatibility. That's the first thing we do. Making sure the temperatures are within our published ratings. We're working within the published pressure ratings, although there may be opportunities to increase pressure ratings by changing the pinch sleeves. So one thing that really hurts rubber is ultraviolet rays, right? So we want to make sure if we're putting these in direct sunlight that we may be coating them or protecting them somehow. And NSF 61 certification is primarily for drinking water, but that's a really big thing we need to check to make sure that we're supplying the proper material. So this is all the stuff that you guys do when you're making valve selections. You want to know what the pressures are, maximum, minimum, nominal. Is there a test pressure? Normal, max, and min temperatures, and nominal, max, and minimum flows, and how often are you operating the valves. So we work really hard on the chemical makeup of processes. So if it's coal slurry, it's coal and water, that's pretty easy. That's going to be natural rubber, unless there's some temperature component that would cause us to go to a different material. So when you come to us, the first question we're going to ask you, or Lesman, we're going to ask you, what's the process? You know, once we understand that, what the pH is, what the solution is, what the solids are, and you don't have to know all of this, but the more of it you know helps us. Is it a powder? Is it a sharp-edged material? Is it fibers? It'll tell us a little bit about what we can expect within the pinch sleeve. Any contaminants? You know, the one of the interesting ones, we do a lot of landfill leachate, and we'll get data sheets that have 40 or 50 contaminants in it. So essentially, we've got to go through there and pick the worst of it, and then start looking for materials that are compatible with that process. So what we find is when we have any kind of failures, in conventional valves as well, a lot of it's got to do with the poor performance of the rubber components due to chemical attack. So we put some little tools together to get us an idea of where we should be heading with elastomer choices. So we have elastomer characteristic sheets. Excuse me. Everybody has one anymore. We all are so mindful of the chemical components of our processes that we're keeping our own data. Now, not only are we keeping data, but we use others' data as well. So the other thing to do, if you have a customer or you are the customer and you're not sure what material to use for a pinch sleeve, is where have you used rubber parts in your processes thus far? Do you have seals in your pumps? Do you have rubber bin liners? Do you have rubber lined pipe? Do you have other lined valves? It's reasonable to assume that we're going to use the same material that you're already using in those components. So this is our elastomeric characteristic guide. This is all published. Now, a couple things that we use. We use the Parker O-Ring Handbook. That's a tremendous resource for deciding chemical compatibility. The DuPont's chemical resistance guide charts are really, really handy. You can sign up for that, and once you do, on their website, you've got unlimited access to their material. And of course, the Zurich has a great deal of material selection data as well. And so if you're our customer, we're going to ask you what kind of elastomers you typically use. Compatibility guides, as I said, really are good. There's some characteristics of processes that give us some trouble. One of them is sodium hypochlorite. It's a very, very difficult, excuse me, process to handle with a rubber material. That's why you'll see a lot of that hypochlorite type process being handled with PVC ball valves, for instance. Sodium hypochlorite, which is used for disinfection, pretty much tears up rubber. And of course, we're looking for materials that are going to resist abrasion. If we looked at a relative abrasion resistance chart, it goes something like this. Butyl is the least resistant of the elastomers we have, going all the way down to natural rubber, which is almost as good as urethane. We do not use urethane right now because of our hand-fabricated process for manufacturing sleeves. We just can't get a material that's compatible with that process. But generally speaking, we're able to handle just about everything that comes our way with the other materials on that list. Storage and shelf life. Because we're a rubber component, We're looking for a cool, dark place to store these things. We don't want them around motors where we might be encountering ozone. And of course, we don't want them stored outside in direct sunlight because the UV attacks the rubber component of the valves as well. So, what do we do with these sleeves? We do a lot of different things. This valve on the left that we call type A is that pinch sleeve in a valve body. The way this product line works is you introduce air into that annular cavity. Air goes all the way around. That air needs to be about 35 pounds over line pressure. So if you have 50 psi process, you need about 85 pounds of plant air. And when you introduce it into the valve, it collapses the sleeve. Now, going back to the first question we got, you kind of see here how far across that sleeve closes. These are typically going to be cast bodies. The valve to its right, this is spun aluminum. This valve is used, it operates exactly the same way. It's a little bit lighter constructed on the sleeve, so it takes a little less operating pressure, but it does allow you to put this valve up in the air in piping systems. It's a lot lighter and a lot easier to deal with physically. What we call a megaflex. This is a type airtight valve or liquid as well that we manufacture 30 inch and up through 84 inch. Operates the same way. Primarily where we use these though is in public works where we're operating with large diameter stormwater lines, combined sewers. We manufacture very small valves, 1/8 inch to 3 inch. This sleeve is a departure from our hand fabrication in that it's molded. So it's one of the few molded parts that we manufacture. And this Type R was designed to be able to just be installed into a pipeline. You can go in small diameter piping, cut a section out, clamp this valve in, and by introducing air through that Schrader valve, you can get this valve to go open close. Now, generally speaking, these valves are air operated. However, you can use city water, you can use bottled gas, any type of medium that you can introduce into that annular cavity to get that sleeve pinched. So, 100% full bore, full port, very, very low head loss. In fact, when a pinch sleeve is open in a full port, full bore configuration, there is relatively no head loss there at all. They're bidirectional. They don't care what direction you put them in line. They close in center line. We get drop shut off. No packing, no links, no levers. The entire wear part of this valve is the pinch sleeve, which is really going to reduce maintenance cost. And again, the sleeve's the only wetted part. They tend to be self-cleaning. So if you have materials that are viscous, if you have materials that tend to scale, I'll give you an example, lime slurry. If you've got a lime slurry that dewaters a little bit and adheres to the sleeve, as you pinch that sleeve, it'll want to break that material off and send it downstream. It's the equivalent of painting a rubber band. You get it painted, you let it dry, you start to flex it, it wants to break off. Same application characteristic of a pinch valve. You can throttle these valves and control them, but they're going to be a little rough. They're not going to be the most repeatable control valves in the world, but you can get rough control out of it. So basically what we're dealing with is a split valve body. There is a gasket laterally down these body halves to make sure we keep that air in. The body functions as the actuator, needs about 35 psi over line pressure to close. You can throttle and control, or modulate, I should say. On off, we're going to use a full port sleeve. For control, we're going to use a cone sleeve, and I'll show you that in a little bit. And again, no packing, maintenance free. And you can also use these for vacuum service. So we have some clients that pull process through the plant. Mostly it's going to be powders, fine fibers, sometimes pellets. So instead of putting air into the valve body, we're going to apply the same amount of vacuum that they're using to move their process into the valve body. That'll give us equilibrium and keep the sleeve open. Once we want that sleeve to close, we've got a continuous vacuum going through the line. We remove the vacuum from the valve body and allow that vacuum to suck the sleeve shut. So it's just operating it in reverse. This will give you a little more idea of how the valve operates. Now, one thing about this graphic, you're going to see a little pipe at the bottom of the valve. We don't supply that pipe. We don't need it for anything because the valve body is an annular space. It goes all the way around. But one thing I can tell you that's beneficial, if you've got wet air, it would behoove you to put a small ball valve down here and go in and drain that valve body out once in a while. So what you're seeing here, full port, full bore, wet with solids, dry solids, chemicals, rods, fibers, pellets, nothing in that flow stream to impede the movement of that flow. And the whole upshot of this thing is, if we can avoid turbulence, we avoid wear. And incidentally, this Type A turned 70 years old this month. Red Valve invented it, was first to market back in 1953 for really Consolidation Coal located in Pittsburgh. So this month is a big deal for us. We're 70 years old. This is what that lightweight valve looks like. The large diameter valves, and you'll see everything is all the same. Just giving you here some ideas about sizes and what we do. The small diameter valves are primarily used for chemical injection, sampling, dispensing lines, and they are a big OEM product for us as well. These pinch valves we've looked at are generally fail open, right? You lose air, you lose liquid, the valves are going to inherently fail open. So what we do is supply backup systems, fail-safe air systems. In the event of a plant air failure, we can keep the valves closed. We apply these to the air liquid operated type valves, also to our control valves. They don't replace any components. It's basically a storage tank, some instrumentation. If we lose plant air, we're able to dump air into the pinch valve and make sure it stays closed. The accessory list for these air operated valves is pretty small. You need a three-way solenoid valve. You need air in, you need air to the valve, and you need to be able to vent. And you'll operate that valve very simply. So no actuators, just an air supply or a liquid supply and a three-way solenoid. If you're going to be modulating or throttling, you will need an adjustable relay, which will essentially take a 3 to 15 pound signal and actually will throttle the air to the valve. Your best friend in the type of valves we just looked at is a filter regulator. One thing about these valves, they don't know when to stop closing. So if you put them in line, you need 35 psi over line, for instance. If you go and give them your full plant air of 120, you're going to really reduce the service life of that valve because of the stress that you'll be putting on the flanges of the valve. In some cases, if you put too much air on it, you'll actually tear the tube off the rubber sleeve flange. So when we say or tell you in the IOM how much air to use to close the valve, we recommend a filter regulator. Set it there, and you'll be good. You may have to move it a pound or two either way. As the sleeve starts to stretch over time, it's going to get a little bit sloppier, and you may need a little bit of air, maybe a pound or two more to close it. But otherwise, that filter regulator will serve you well. So options and accessories. I mean, fail-safe air packages, any kind of coatings, whatever the coating specification requires, that's what we do. And of course, I don't know if you run into this at all, but any of the AIS, Buy America, Buy American, we comply to all of that. And just to give you a little bit of idea of scale, this was a 64-inch air-operated valve that we put in a desalination plant at the Dead Sea Works. This was handling very highly concentrated lime. And the reason they went with this valve is the pinch sleeve isolated all the mechanical parts from this very high chloride process. And these things have been in there now since the 90s. So, manual valves, same story. Pinch sleeve, but now we're just going to take and mechanically operate this valve. So the two valves that we started with were the Series 70 and 75. You'll notice the open frame construction and one with a closed body. These both work the same way. When you turn this hand wheel, this tom pitch bar goes down, this yoke comes up and pulls this bottom bar with it. So these valves close on the center line. And again, the idea there is to try to keep flow as smooth and laminar as possible in order to avoid turbulence, because turbulence causes wear. The open frame valve is almost exclusively used in applications that are powders, pellets, fibers, and mines like them. And it's a little unusual because if that sleeve breaks, that process is going to just go all over the place. But the mines have traditionally liked these because they can see them from a distance. They know what's going on. Is the valve open? Is it closed? And it also allows us some flexibility with length. If you'll notice, the side rails of this valve body are just rod. So if you had an odd opening, for instance, if you needed a valve that was 6 inches longer, because we hand fabricate that sleeve, we can make that sleeve 6 inches longer. So your valve now just drops straight into that line. It's not done all the time, but we do have a few clients we do that for. We generally do not make valves shorter than the length we publish. And again, it's because we're pinching these valves and we don't want to tear the flanges off the tubes. So there is a limit to how short we can build things, but not much limit to how long. So then we have an option for a closed body valve. That valve is primarily the valve we're going to use in liquids. In case you break or the sleeve ruptures, we're going to at least be able to direct that flow either into a floor, into a drain, or keep it from spraying all over the place. It's a pretty simple matter to make this valve suitable for direct earth burial. And we've also taken the opportunity to turn some of our control valves into manual valves. So these three at the end, we'll see those again here in a minute. So these are what these valves look like. We do these valves through 48 inch in the open frame, through 12 inch in the closed body, and over 12 inch, we just use a different valve body. These are the varied valves. Torque tube, as you see here, usually operated with a gear. You can mount an electric motor on there. If push came to shove, we could do hydraulics. And because of that, again, back to that sleeve capability where we can manufacture sleeves to 300-pound class, we provide a high pressure type valve for 720 psi as well. And if you look at this, we won't go through this whole thing, but this is basically all the same features and benefits that you would see in the air-operated type valves, with the exception of a couple. There are no packings in those valves we just looked at. There's no packing required because the sleeve isolates process from the mechanical parts. And as I mentioned earlier, opening and closing torques are going to remain the same over the life of the valve. That's pretty much what a manual valve looks like in a bidirectional close. All the options you can get on conventional manual valves, we offer the same. Bevel gears, floor stands, chain wheels, operating nuts, coatings. We can apply limit switches, lockouts, tagouts, all of that's available. So, control valves. Now what we're going to do is we're going to actuate these valves. Again, all the features and benefits of the pinch sleeve come with the control valves as well. But now we're going to be able to offer repeatable and accurate flow control, because we're using mechanics to move that pinch sleeve. So the air liquid type valves are very difficult to maintain repeatability, because any change in your air pressure, for instance, changes the position of the sleeve. In the case of these control valves, we're using mechanical mechanisms to take the pinch, and we'll bring them back to the same place every time. So they're repeatable, accurate. In most cases, except for cone sleeves, they're bidirectional again. They don't need flange gaskets, no packing. There are external stroke adjustments, which we'll look at in a second. And here's what basically a section on that valve looks like. The pinch sleeve that we've been discussing thus far, a pinch mechanism. In this case, this valve is, you could tell it's 1 to 4 inch, because we're pinching directly from top to bottom. Positive opening tabs. We also manufacture the pinch sleeve to be attached to the pinch bar. That gives an assist when we go to open that valve. One of the biggest features, and one of the most important, is this external stroke adjustment. Over time, when you're dealing with a slurry, that slurry will start to take away some material on the inside of the sleeve. So what will happen is your sleeve ID will start to grow. So you have that pinch bar, say set to stroke 4 inches. And now your ID has grown due to wear to 4 1/32. Well, you're going to get leak by. But the sleeve is still good. The sleeve is still good to use. You would operate that external stroke adjustment, take up that 32nd, and you're good to go again. Cylinder operated valves, open frame, closed bodies. This valve was an early day centerline closing valve. It's very complicated, it's very heavy, but we do get some applications for it still in the mines. What basically happens is when we actuate this valve, the shaft pushes a top pinch bar down. This lever and linkage pulls a bottom pinch bar up, and we close on the center line. So some of the valves we close directly, some of them we close on a center line. Generally speaking, we're always looking to use a center line closure on valves that are very, very low velocity solids bearing lines. Because if the velocity is too low, the solids will fall out. So we want to keep the inverts of those valves as open as possible. So basically, these centerline closing valves, as they are named, close on centerline. We also take the same design, and now we're not going to actuate this valve. This valve will have a spring included, a range spring adjustment, and we use this valve as a pressure relief valve, say in a bypass line. So we can take and set this spring to keep the valve closed at a set pressure. When your process exceeds that set pressure, it reverses the spring, the valve will pop open, allow that pressure to dissipate, and then the valve will come close again. So now for slurry service, you've got a pressure relief valve with no mechanical parts in the flow stream. Now, this is kind of interesting. We had this valve out a long time ago, and we pretty much abandoned it. And our competitors came back and they started using it, so we revived it again as well. This is another version of a centerline closing valve, but this time the entire actuator is going to lift up. So when we actuate this valve, the shaft comes down, pushes a bottom pinch bar down, the entire actuator rises, and via these side rails, we pull a bottom pinch bar up. Pneumatic, electric, hydraulic, all of these actuators are available on these valves. So I'll give you a little bit of an idea how this works. And again, the whole idea is to keep the sleeve as full ported, full bore all the time, and close on the center line in order to give us a nice, smooth closing action to reduce turbulence. Electrically actuated valves. Again, everything starts with a pinch sleeve, either open frame body, closed bodies, and again, finally, the Series 9000s that are 300-pound class. Again, all the actual options and accessories that you would use on a traditional valve, we use as well: positioners, limit switches, lockouts, tagouts, floor stands, you name it. Fail-safe air tanks are used with control valves as well. Now, I mentioned to you customization. Here's a 24-inch valve for the Phoenix mine in Nevada. These are tailings valves, right? So you can barely see them, but here, all the way around to the horizon are pinch valves on spigots. They wanted some crossover valves to be able to control where they were going to put flow in order to balance the tailings discharges into the pond. They had 200 psi shutoff pressure. Our standard operating pressure is 50 psi. So we managed to build, without a whole lot of trouble, a pinch sleeve for 210 psi, but it was so thick we didn't have a valve body for it. We used an open frame, channel construction, hydraulically actuator to be able to handle that type of flow. So there's a lot of customization available. So sleeve styles: cone sleeves for modulating, throttling, full port for on-off, open close, and double walls, which are actually 3 thickness for high abrasives. Now here's this cone sleeve. So what you find out right away, if you were trying to control with a full port, full bore sleeve, is it's too big. If you take that full port, full bore sleeve and pinch it 30%, you haven't changed the cross-sectional area at all. You have turned a circle into an oval. What that means is you're typically working in an operating range of about 70–80% or more closed. And what ends up happening is when you pinch that full port sleeve, it ends up looking like a funnel. Oh, I'm sorry, an hourglass. So you'll get a nice control in the middle. The problem is your slurry will come through, hit the pinch point, your pressure recovery will go turbulent inside the valve, and the valve will fail very quickly. What we found out years ago was we needed to characterize that trim in order to, number one, get rid of that 30% that doesn't get us anywhere. So you've all been most likely in places where you've seen a 4-inch valve and a 6-inch line. We could do the same thing, but we're doing it this time inside the valve. We get a lot better control. So cone sleeve advantages, lower CV values, inherent pressure drop because of the geometry. We build that cone reduction to put you right in the sweet spot of your flow. So you don't have any slop in there between the time you start to pinch that sleeve and the time you get to where you need to be in your control range. It can handle higher pressure drops, and because it's got all this material down here downstream, you're going to get a much extended service life out of that sleeve, and it gives you much, much more precise flow control. So to give you an idea of what happens here, if we had a 6-inch full ported pinch sleeve and our desire was to get a 450 CV, that sleeve would only be 18 inches open. So flow would hit that vena contracta. You'd get a little control there, but the problem will be when the pressure recovers and goes turbulent. Just by taking that sleeve and reducing it to a 6x5, we get the 40% open. That reduces all that turbulence, and it allows the pressure to recover downstream and not in the valve. If we go to a 6x4, the valve's 100% open. So the cone sleeve gives us a lot of leeway on how we design for flow control. So full port sleeves, 100% full port, full bore, bidirectional. Double walls, as we said, are actually a triple thickness. The elastomers we looked at previously. Now, this is a little bit of an odd device, but it goes along with our control valves. Every now and then, particularly on applications where we're discharging to atmosphere, we're taking 100% of the pressure drop. We need to apply a little bit of back pressure on the valve in order to put it in its control range. There are a couple ways you can do that. You can put another valve downstream, start to close that valve, and put your control valve back where it needs to be. This valve is actually a backflow preventer we invented in 1984, whose stiffness we can change in order to make it a back pressure inducing device. I won't go into this too much, but you can read a lot more about it in our control valve data. We came up with, over 25 years ago, a sizing program in order to size cone sleeves and sleeves for control valves. This is all the information that you would either get or put on your control valve data sheets. We're not doing anything different than what would appear on an ISA data sheet. And we enter all that data, however it comes to us. We apply it to our program, and what it does is it tells us the size of the cone reduction to get us into the optimum control range for the application. All this is available. We do all this for you as a service. So, applications: wastewater, mining, chemical, pulp and paper, power. You know, we talk about wastewater as if it's a different market, and it is. It's a municipal market. However, some of our largest business comes from industrial water and waste. So we want to be mindful of those applications as well. But mining from tailings to flotation, lime feeds, thickeners, cyclones and hydrocyclones, likewise with power. And remember, a lot of times in the chemical market, we can have a very, very pure chemical that's very, very aggressive to metals, and a very simple rubber material may preclude you from having to go to an exotic metal for your valve internals. So it'd be worth looking at. And of course, the wastewater applications, grit, clarifiers, scum and grease, sludge, all kinds of flow diversion. No, plastics, right? Bulk handling, conveyance, pellets, fibers, powders, specialty chemicals. We've got a brisk market in industrial stormwater as well these days. Another big application industrially at some of these facilities is raw water intakes. Sticks, stones, rocks, anything you're liable to get in your raw water lines won't cause us a problem. And likewise, power. I would tell you lime slurries probably is the biggest application worldwide we have. It's everywhere, and primarily for neutralization. But pulp and paper, mining, of course, and that's it.
Thank you, Chris. You know, we had questions throughout the presentation, but you did such a thorough job. You answered every one throughout your presentation. So with that being said, we're up against our time limit. So I want to thank you, Chris, for your education. I want to thank the people that have joined us. Again, this is going to be recorded for those who can listen to it later. So with that being said, I'm going to end the presentation and thank you all for your attendance. Have a fantastic day.
Thanks, everyone.